one more time, we changed 2 over x into 2 times x to negative 1, and we found the first derivative.
Okay.
And then d2y over dx2 will be 6x minus 4x to negative 3. Is that okay?
Yes.
Then d3y over dx3 will be 6 plus 12x to negative 4. And can anyone dictate the last one?
It's negative 48 times x to the negative 5.
That's it.
So you're just finding the derivative. Just finding the derivative until you finally get to the fourth level of derivative. Oh, all right. That's not so
Good. Excellent. That's what I wanted to hear. I reached my target when my students say that. Good. Anything else that you would like to go back to? Anything else you would like to review for the test on Saturday morning at 10 a.m.? You can always stop me at any point in time if you remember something.
Can you do
Yes?
something that involves the chain rule?
Yes. Excellent question. Jess, aka Michelle. Don't call her Michelle, it's not her name.
Oh, that's a good thing.
Just one time I called her Michelle because she looks like another student, and her name is Michelle. Okay, so let's say the cube root of x squared plus 2x. If I want to differentiate this, first I will change it into
Everything
x squared plus 2x raised to,
1/3.
very good. I bring 1/3 in front, subtract 1 from the power, and times the inner function prime. I bring down the power, subtract 1 from the power, and multiply by the inner function prime. Okay, so let's say you forget this. You forget the formula, right? Here's what I would like you to remember. When you differentiate x to the fourth, what do you write?
4x.
To the,
second.
and you should write x prime. This is the formula. Power in front, subtract 1 from the power, and I differentiate the inside. But we don't write this. Why do we don't write it?
It's 1.
Because it's 1, but it's the same formula. And now all you have to think of is just replace this inside by this. It's the same formula. We bring down 4, subtract 1 from the power. We bring down 1/3, subtract 1 from the power. And here we have a function. When we differentiate it, we get this. But when I differentiate this, I get 1. But it's the exact same formula. Better? Yes,
Yeah.
please. April, go ahead.
I'm not sure if I'm explaining it right, but when we have like the average cost,
Yes?
and then we differentiate that, and
Yes,
then
the
have
average cost-
rate of cost.
Because of the average cost function has to be determined.
Right.
It's the cost over x. So it's a totally new function. And now when we want to find the rate of change is the derivative of this new function.
Okay, that's what I have.
So when I'm asked to find the average cost, I have to create a function c of x over x. When I'm asked to find the average of that function, I have to differentiate it. The rate of change of that function, I have to differentiate it.
I think what happened last time was we had like 50x, and then 50x over x was just 50. So, but if you differentiated it,
If
it was
I-
50. So I think that's why I was confused to begin with that one problem.
Okay, but is it clear if it says the average cost, then you have to divide by the number of units?
So cx over x,
Yes.
px over x, and then
And if you're asked to find the rate of change, it must be the derivative
the derivative of the new.
of the average, yes, of the average cost.
Okay.
If it says the derivative of the cost will mean, well, if you're asked to find the derivative of the cost, it will ask you to find the rate of change of the cost.
Okay.
Not find the rate of change of the average cost.
Okay.
But if it says of the average cost, then you are differentiating C of x over x, not the cost.
Okay.
Good. Anything else that you would like to go back to for the test? I would redo all problems we did in class, please. Can I start chapter 2? You can stop me anytime if you remember something, or I say something that triggers your memory on the past problems or past topics. Stop me, okay? So chapter 2. In chapter 2, we are going to look at applications of differentiation. Applications. Applications of differentiation. In other words, why we even study differentiation. Uh, 2.1, we're going to look at max-min of functions. And you can say, again, haven't we talked about max and min before? We have in algebra, etc., etc. True. But this is a more in-depth discussion, and now we have tools that we did not have before. Okay, so let's take a look at this function. What we know from algebra is that it has in here somewhere a relative max, and in here somewhere a relative min. Would you agree? So this must be relative. In some books it's called local max. And this is definitely a relative or local min. In order for a function to have a maximum, obviously it must do what? It must
Increase.
Awesome. And then it must
Decrease.
And then in order to have a minimum, a relative minimum, it must first
Increase.
and then must. It's obvious, right? Okay. So let's analyze one more thing, and then I will look at a definition, very important definition. Okay. So let's suppose at this point I draw a tangent line. Then at this point I draw a tangent line. And then at this point I draw a tangent line. And at this point I draw a tangent line. And then this point I draw a tangent line. And at this point I draw one. And at this point I draw one. And I continue. What is the slope of the tangent line at max or min? How much?
Should it be 0?
Of course, it's horizontal. The tangent line at the max and the min is horizontal. A horizontal line has slope 0. Very good. You told me here that the function is increasing. What is the sign of the slope every time the function is increasing?
Positive.
Correct. What is the sign of the slope every time the function is decreasing? Awesome. So I could write, and please agree or disagree, f increasing means f prime positive. F prime positive means f increasing. F decreasing means f prime.
Negative.
So for now we established that idea. Here is the next concept. Critical number, or critical numbers, better. Critical numbers. What am I trying to do? I'm trying to find max min for functions. only critical numbers of a function can turn into max-min. I'm going to put that in writing. We don't even know what a critical number is yet. But note, only critical numbers can turn into max-min for a function, of a function. There is no guarantee, though. So if I found a critical number, it doesn't mean that that critical number is a max or a min. But only critical numbers can turn into max-min. So only critical numbers can turn into a max or a min for a function or of a function, and there is no guarantee. Okay, now let's see what a critical number is. A critical number comes, I can write tonight, as you see. A critical number comes from two possible sources. A function can have critical numbers coming from both, or none, or just one. Number one possibility is f prime of x is 0. The second possibility is f prime of x is undefined at x values where the function is, where f of x is defined. Okay, let's summarize let's go back to the beginning. Critical numbers are very important. If a function has no critical numbers, that function will not have max-min. If a function has critical numbers, I don't know if they change into max-min. I have to study the function. It's not enough. There is no guarantee. Critical numbers are those x values that make f prime being 0, or they make f prime being undefined where the function is defined. If the function is not defined at 2, the derivative will not be defined at 2, so there is no discussion there. But if a function is defined at 2, but the derivative is undefined at 2, and something very important happens there, this is not the whole story, then that could be a critical number because the function is defined at 2.
So anything 0 over 0, or a number over 0.
Very good question. Very good question. No. So the question is, when I'm thinking of an example in which the function is defined at the x value, but the derivative is not defined. Okay. And that becomes a critical number. We talked about this. This will be very clear for you. So here it is. F of x equals the square root of x, correct? Mm-hmm. We already know the derivative. We don't have to prove this. It's embedded in our brains already.
1 over 2 square root of x.
Excellent. Okay. Where is this undefined? At
0.
Exactly. Is the function defined at 0?
No, it is.
The square root of 0 is 0.
Yeah.
The derivative is not defined at 0. 0 is a critical number because the function is defined at that point and it will turn into a minimum. Here's the graph. So the function is not differentiable here. At 0 is not because the derivative is undefined. This is a critical number, 0. The function exists at 0, and this turns out to be a minimum. Furthermore, it's the global minimum. More than, it's not a local. At the end of the interval, we don't have local or relative. because I have to be able to show the open interval. The function must exist on both sides for a relative or local.
It has to be in the middle of the function to get that.
Correct. Exactly. It cannot be at the endpoints. So the derivative is undefined. The function is defined. This is a critical number, and yes, it is a minimum.
But it's not a local minimum.
It's not a local minimum. This is an example of when the derivative is undefined, the function is, and that is a minimum. Very good question. Okay. I would like to show how this works. Your book calls them critical values instead of critical numbers. They are called critical numbers, but you can call them critical values. You are allowed to. Okay, on page 201. I just want to find critical numbers for now. Problems 1 through 34. Page, one more time, 201. Very good. So let's look at 13. F of x equals 1 minus x to the third. In number 1, we're asked to find critical numbers. Find critical numbers or values, since your book uses values, not numbers. What do I have to find first? The derivative dictates the critical numbers. F prime of x. So this is negative 3x squared. I know that critical numbers come from two possible sources. One, when f prime is undefined. Does that happen here?
No.
Because the derivative is a polynomial, this will always be defined. F prime will always be defined. It's a polynomial. The other possibility is f prime of x to be 0, which means negative 3x squared equals 0, which means x equals perfect. How many times? 2. You'll see what happens. So for now, this is a critical number. X equals 0, critical number. Do I have to write it twice? No. I was just making the point. Now, does this turn into a max or min? That's the next step. And then we'll come back and choose other functions, but I would like to continue with this one now. Okay, so that's my next question. Is x equals 0? Or does x equals 0 create a max min? That's the question. Will this turn into a max min? Let's go back to our graph. Obviously, this graph has a max and a min. What is the condition here? Which we already established, f prime to be 0. But the condition here is that on this side, the derivative has what sign? And on this side, immediately past the maximum. So in other words, I'm telling you this. That could be a critical number. Would it be a max or a min? Only if the derivative changes signs. You will have a maximum if it changes sign from positive to negative. You will have a minimum if it changes from negative to positive. If the derivative does not change sign, even if there is a critical number there, that's not a max min. So here's our next step. We create a little table. F prime being the first, and f of x following it. X is all real numbers, I hope you agree. This function is defined on all real numbers. It's a polynomial function, right? Good. And that's 0. The derivative is 0, right? F prime. Careful, I use the lowercase like I always do instead of the uppercase, but you know what I mean. It's the uppercase f. That's the name of the function. It doesn't matter really. Okay, so f prime of x is 0 when x is 0. So now the question is, what is the sign before and after? That will dictate, that will tell us whether this changes into a max or a min or none of the above. So studying the sign of the derivative and being able to put a sign here and a sign here will tell us whether this is a max, a min, or no point of extrema. Good. So let's look at the function. Here's the derivative. What is the sign of the derivative for any number to the left-hand side of 0? Pick a number, plug it in, and tell me just the sign. I don't care for any value, just the sign. Of course. Pick a number, 5, 10, 11, whatever you want, plug it in and give me the sign. What do we conclude? This point 0, comma, and I should determine it. When x is 0, y is 1. The function value is 1. So I'm going to write 1. What will you say about 0, 1? Is it a point of max? Is it a point of min? Or not a max or a min? Of course, the derivative does not change sign. It continues to decrease all the time. How can it have a maximum? How do I know it decreases? Negative all the time. Negative, 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 negative. It does not turn. It cannot have a max or a min. It never turns. The function is always decreasing according to the sign of the derivative. There is no point of extrema. We're going to do the same thing. Please choose any other function you want. Anything. So, yes, which one? 26. 26. Find any relative extrema of this function. So that's, I should have read this from the beginning, but I just always focus on the critical number. List each extremum along with the x value at which it occurs. Then sketch a graph. I'm not going to sketch the graph. We don't have enough information yet. We will sketch graphs a lot. But not at this point. We're not ready. Okay, so we chose 26. Where are you, 26? I see it. X plus 3 to 2/3 minus 5. And this is our f of x. Good, perfect. So we're given a function. We're asked to find whether it has a max or a min. My very first step must be the domain. For any function, the domain. But this is the cube root. The cube root, right? This is the same with the cube root of x plus 3 squared. The cube root is a very friendly root. Any index that is odd is a friendly root. No restrictions outside, no restrictions inside, anything goes. So this is defined everywhere. The square root, the fourth root, that's a totally different story. Perfect. Now, what do I have to find? Either to establish whether this has a max or a min, I must find. That's it. I bring down 2/3. X plus 3 to 2/3 minus 1 times the inner function prime, but it happens to be 1. The inner function prime is 1. I don't have to do anything. And the derivative of -5 is? Excellent. So now I will change this into 2/3, the cube root of x plus 3. Take a moment and say, yes, I agree, or no, I don't. I got 1 vote. Anyone else? Good, I got 2. Do I have 7?
Is it negative or no?
If the power is negative, it doesn't mean that the answer is negative.
Okay.
A negative power only tells us to bring that quantity in the denominator. Good. So now, critical numbers come from two sources. From f prime being 0, or from f prime being undefined, where the function is defined. That's one of the reasons why I always have to start with the domain, because you never know. Ready? Okay, so let's look at this fraction and set it equal to 0. And now I'm going to ask you, what do you think? You should ask me, you lost your mind. A fraction is 0 only if the numerator is 0, so this can never be 0. Goodbye. So then, let's look at f prime again. And let's say, is this function undefined for any x value?
X equals 0.
0 plus 3 is fine. When x is?
Negative 3.
Excellent. Yes, so when x equals negative 3, the function f prime is undefined. Now I'm asking myself what immediately? Is the original function defined? Because if the original function is not defined at negative 3, that's not a critical number. Is the original function defined at negative 3?
Yes.
Yes, so this is a critical number. So now let's go back to our table. F prime of x, f of x, all real numbers, negative 3, undefined. There is nothing I can put in the row for f prime. Under negative 3, there is nothing. Okay, so now let's plug in negative 3 here and tell me the function value so I can put it here. In the row for f of x, negative 3 plus 3 is?
0.
0 raised to 2/3
0.
minus 5.
Negative 5.
So the discussion now is about the point negative 3 comma negative 5. That's our question. Whether this is a point of extrema, which means max min, or not. Okay, so I have to go back to the derivative and study the sign. Okay, so let's plug in negative 10. Negative 10 plus 3.
-7.
The cube root of negative 7, is it positive or negative?
Negative.
Excellent. So what is the sign of the entire thing? Great job. Now let's plug in the first derivative, a number like 0. I can. Any number between these two, 0 or anything else, just plug it in. I don't need any calculations. I only care for the sign. So, what is our conclusion?
That is a minimum.
Exactly. It is a minimum. Why it is a minimum? Because on this side, the slope is negative. Here, it must be undefined or 0, whatever. And on this side, it is positive. And this is typical for a local min. Guaranteed. Any questions? Any questions? What else can I say about this function? I will say this. Like for the other one from before, I explained it, but I didn't put it in writing. So let's write it for the other one. F prime of x less than 0, f always what? F always, when the first derivative is always negative, F is always, very good. So now I will say, which we couldn't do in algebra. In algebra, we were just looking at the graph and we said increasing here, decreasing there. So now we'll say F increasing on, can anyone give us the information? F increasing on which interval?
-3 to +infinity.
And F decreasing on which interval?
-infinity.
Very good. I can say that now. Okay. I would like to look at a word problem in a minute. Advertising, solar eclipse, life expectancy. They're on page 202, 203. But before that, I would like us to choose a problem from 69 through 82.
76.
So 76 is on page 202. Very good. So here's the question. In 76, create a function. It says draw a graph to match the description given. There is more than one correct answer. So in 76, we have g of x has a positive derivative over f, is g prime positive over negative infinity negative 2 union 4 comma 7, and negative g prime of x is less than 0 over negative 2 4 union 7 to infinity. This is the information given. And we're asked to graph a sample, an example of a function that fulfills the given conditions. Like before, I strongly recommend create this table. So they're all, I'm going to make them all lowercase. They're all the same. I'm going to put in the table, of course, negative 2, of course, 4 and 7, infinity and negative infinity. This is g prime. And of course, like always, the second row is g. And I summarize the information I have in my table. Between negative infinity and negative 2, it says it's positive. Between 4 and 7, it's positive. Between negative 2 and 4 is negative. And in between 7 and infinity is negative. Therefore, when I graph a function, again, there is more than one correct answer. When I graph a function fulfilling these conditions, how will I graph it between negative infinity and negative 2?
Increasing.
Very good. How will I graph it between negative 2 and 4?
Decreasing.
Between 4 and 7?
Increasing.
And then decreasing. Now you have several options. You can make this negative 2 whatever number you want to be undefined for the derivative, in other words, or be a maximum. It changes sign. Here, if you would like to consider a point, what type of point will this be? Very good. And this one, the last one, what type of point will it be? It changes the sign, it changes between positive and then negative. Maximum. Very good. So let's give it a shot. And here it is. 1, 2. This is negative 2. 1, 2, 3, 4. This is 4, 5, 6, 7. I had to make sure that I had in the coordinate system the -2, 4, and 7, because they are important points. And then increasing till whatever you want. Then it's decreasing. You could have graphed it with a maximum, or like I graphed it, with an undefined situation. The derivative here, it's a corner or a cusp. The derivative does not exist, but it's a local max because the function exists. Okay, then I have a local min. I can continue like this, or and decrease, or I can continue like this and make it a maximum, whatever you want. As I said, there is more than one correct answer. We were not told to use undefined situation or max min. We did whatever we wanted.
So if it's undefined, it would be a corner or a cusp.
But it still has to be continuous.
But it will be continuous. But
Yes.
if it's 0, it will be like a hill.
Yes,
Yeah.
you could have made it. So you can. So you can make it like this.
So if they tell you that all your minimum and maximums are zeros or undefined,
It doesn't say. You do whatever you want. But you cannot do both. So let me erase one or the other.
you can mix them.
Yes, that's what I did. So I kept this one as a f prime undefined, and this one as f prime 0. Very good. So before we move on, I'd like to at least look at one more problem. Like 88 on page 202. Because I want you to see an application of this. And no, we're not ready to graph. I know they're trying hard, but no, not yet. I disagree. Advertising. Brody Electronics estimates that it will sell n units of a new toy after spending thousands of dollars on advertising. And we are given the function n of a. A is the number of toys, n is thousands of dollars. No, n units, and a is thousands of dollars. Okay, a. And this is 88 on 202. And n is the number of units. Negative a squared plus 300a plus 6, n number of units predicted to be sold. A between 0 and 300. 300,000. Find the relative extrema and sketch the graph. Forget about the sketch in the graph. Not now, not yet. In a minute, we will. So for now, we want to find whether this function has a relative max or a relative min. What do I have to find?
The derivative.
N prime of a, negative 2a plus 300. There is no point for this function to discuss n prime being undefined, right? It's a polynomial function. The derivative as a linear function will always be differentiable, and this will always exist. So critical numbers will only come from n prime of a being 0, which means negative 2a equals negative 300, a equals 150. A equals 150, or 150 is a critical number. Beautiful. But I don't know whether this is a max or a min. There's no guarantee. If you remember, a few minutes ago, we had an example in which it was very nice. We did determine a critical number, but the derivative did not change sign. Even if it's a critical number, if the derivative does not change sign, it's not a max or a min. So therefore, I create the table A, n prime of A, and n of a. 150, 0 to 300, because we are given that interval. What do I write under 150 for n prime?
0.
Perfect. I should find n of 150, because I need that point. Can anyone give us n of 150?
Uh, 22,506.
I'll write it down, 22,506. 22,000.
506. That doesn't sound right.
Okay, let's do it again. That's okay. So negative 150. And then we have to square that, plus 300 times 150, and then plus 6. 22,506, you're right.
That's right.
Units. N is units, very good. When 150,000 are used, spent on advertising. Very good. Okay. So now I look at this, the derivative. I see it's a linear function. I will plug in 0. 0 is a number here. Just give me the sign. Excellent. Now please plug in 300 and give me the sign, just the sign.
Negative.
Very good. Which means this is a typical situation for what? Indeed. So what would you say to this owner of the advertising agency? What would you tell him or her? You will say, if you want to maximize the number of units sold, please spend $150,000 on advertising, and you will maximize the number of units. If you spend 100,000, you're gonna get less than 22,506. If you spend more, it's a waste of money. You're not gonna get more than this, because the function starts decreasing. Questions? Questions? Okay, I am ready to move on. I will also explain what it's called the first derivative test and the second derivative test.